Log on, tune in, find out. Another good idea from Cambridge.
Yeah, Soibelman from Kansas State, and he's talking about integrable systems, mirror symmetry, and DT invariants.
So, thank you very much. So, thank you for giving me an opportunity to speak here at 9:30. And my special thanks to organizers who put my talk on my birthday, so it should be devoted to myself, probably. At the end of the talk. So I'm going to talk about some ongoing project with Maxim Kontsevich, which is devoted to the relations between different topics, complex integrable systems, mirror symmetry, and the theory of motivic and numerical Donaldson-Thomas invariants, which we suggested some time ago. And since today is basically sort of a Donaldson-Thomas invariants day, I recall you that in that paper we advocated the idea that Donaldson-Thomas invariants, in the way we introduce them, should be encoded into the structure of complex, or maybe more generally non-Archimedean symplectic manifold. So the numbers are not visible. They appear when we look for the way to glue this, for example, complex symplectic manifold from simple pieces. All right, so the reference for, so let me give you two references for this Donaldson-Thomas story. And although I will be using very little today from those two papers. But let me start recalling the classical Liouville integrability, which, since I will be talking about real and complex integrable systems, I should at least recall you what they are. So classically, so it's like Liouville integrability. So we start with a symplectic manifold. So then the algebra of functions carries a Poisson bracket, and so the conditions of the Liouville theorem says that we have a collection of functions, so let it be 2n-dimensional, and functions generically independent, which are Poisson commute. They are involution, and then we have a map M to say Rn, given by this collection of functions. So when the fibers, just assume that the generic fiber is compact, then the theorem says that the fibers are compact. And so then this generic fiber is a Lagrangian torus. So this is a classical story. Of course, we can generalize a little bit and consider instead of Rn here anything. Like n, 2n. This is n-dimensional, and we work, for example, in the category of smooth manifolds. All right. Now, the complex version of the story is similar. So this is basically, by definition, the real integrable system is given by such a map with a generic fiber, which is a Lagrangian n-dimensional torus. And certainly, if we pull back functions on the base. We get a commutative algebra in the algebra of functions on M. And so this leads, of course, when we think about quantization of this story, so this leads to the natural notion of quantum integrability. In this case, we replace algebra of functions on the phase space by its quantization, some non-commutative algebra or maybe sheaf of algebras. And so integrability is understood as existence of a big commutative subalgebra inside of it. So this is also a very classical story, although it's quantum. Now, complex integrable systems, it's just a variation on this subject, although there are some new features, but the definition is basically the same. So we have now a complex 2n-dimensional manifold. The symplectic structure is, say, holomorphic. The base, this is called the base of integrable system, is also holomorphic. And the generic fibers, this is again, this is a definition. The generic fiber, which means smooth fiber, is a complex torus, compact complex torus. So a special subclass which is relevant to geometry and which was studied extensively in the middle of 90s. From this point of view, it's algebraic integrable systems. So the fiber is abelian variety. So complex Lagrangian, sorry, I forgot. Abelian variety. Okay, so you see that the ground field is not very important here, at least at the level of definitions. So, and in practice, one can meet integrable systems which are not real or complex in mirror symmetry. One meets integrable systems, so one sees integrable systems over more general field, in particular over the non-Archimedean field of Laurent series, or more generally Novikov field. And in the course of constructing of mirror dual. Now, so if we have, say, a real integrable system, so then automatically on the smooth part, on some open dense part of the base, we have an integral affine structure for the obvious reason. So if we have a real integrable system, then we can, for example, choose a basis in the first homology of the fiber, integrate symplectic form, so then we get a collection of exact of closed one forms on the base, and locally we can resolve, we can find the functions solving this system of equations, and they are affine coordinates. So then we have an integral affine structure on the smooth part of the base. smooth, because in order to do all that, we need to have a non-degenerate fiber. And of course, the integrable system, although generically the fibers are Lagrangian tori, but almost always we have some degenerate locus. In the case of complex integrable system, this degenerate locus has a complex codimension 1, so it has a real codimension at least 2. All right. Now, there is a special class of real and complex integrable systems which correspond to trivial, to the exact symplectic manifolds, and I will be discussing mostly the case of complex integrable systems, because our results are more interesting in this situation. So these are what we call complex integrable system of Seiberg-Witten type. In the case of complex integrable systems, if you perform the similar construction, you'll get too many closed one forms. And so there is what is called special geometry. There is a dependence between complex affine coordinates, I would say. And so in the case of Seiberg-Witten integrable systems, so we can define globally, so this implies that there exists a global section on the smooth part of the base, so it's smooth, non-degenerate fibers. This is a definition of smooth part of the base. And this section can have a monodromy, and monodromy comes from the local system, which I just erase. So you can consider the local system of lattices, so the corresponding something like this. So there exists a section of this bundle such that for any fiber, or maybe let me say for any local section, the differential in gamma is equal to this integral. So for the reasons which are clear for people familiar with stability conditions, the notation and the name, so this should be called central charge. And indeed, for any smooth point on the base, it defines a homomorphism of abelian groups. So it can be thought as a collection of homomorphisms of abelian groups. So and since the fiber, let's assume, for example, that it's, well, since the fiber is a torus, so there is a symplectic structure on the lattice. So these are exactly the data from which one can start this machinery of wall crossings and so on. So gamma B carries it's not very important that it's symplectic, but it turns out to be that it's symplectic. And so therefore one can construct this well-known Lie algebra of Poisson algebra of functions on the torus of characters. And then in order to see the rest of the wall-crossing package, one needs to define a collection of integer numbers, which I will discuss a little bit later. But this is just for people who really want to see some relation to the wall-crossing right away. Now, of course, there are tons of examples of real and complex integrable systems. It's industry and industry inside of industry. There are many examples of Seiberg complex integrable systems of Seiberg-Witten type, those which have central charge. For example, Hitchin integrable systems, they are of Seiberg-Witten type. And so the central charge, basically if you have a spectral curve somewhere, then you should look, of course, for this data. In the case, in Hitchin case, when you have a spectral curve, then of course you have the one form, a restriction of the canonical form to the spectral one, and so it gives you the central charge. So Hitchin is Seiberg-Witten. And of course, Seiberg-Witten is Seiberg-Witten. So this famous examples which were popular in the middle of 90s and studied by, for example, by Donaghy, Markman. In the case of probably more closely related to Hitchin, there was a paper by, I think, Diaconescu, Donaghy, Pantev, and previously there was a paper with another D who was a digraph, and they proved the following result, which, by the way, maybe it's useful to keep in mind. They proved the following theorem that ADE Hitchin systems are realized as families of intermediate Jacobians of non-compact, certain, they describe them explicitly, non-compact Calabi-Yau threefolds of a conic bundle construction. So, and in our paper on Donaldson-Thomas invariants, we speculated how this kind of results or similar results by Donaghy and Markman, where the integrable system is not algebraic because it's associated with compact Calabi-Yau, how they can be generalized to arbitrary three-dimensional Calabi-Yau categories. For example, I think it's still open question. So it's a question how to construct, how to generalize to the case of quiver with a potential. So this is a quiver, this is a potential, which means polynomial in arrows which is cyclically invariant. So this is of course very simple, quiver and no potential at all. Okay, so let me formulate some results. So basically this is a ongoing project, and I thought that I would be using some preliminary draft of what is done, but since it changes every day, so probably it's impossible to use it. I will formulate some results, part of them as theorems, which means that we are closer to the proof. And some of them conjectures, and you can guess what does it mean. All right, so in order to be more precise, I will formulate a theorem which starts with the word under some conditions. And since the discussion of the conditions will eat the rest of my talk, so under some conditions, I will discuss it. So I will do the following. I will formulate something, and then we'll discuss the relationship to mirror symmetry and so on. But let's just, in order to formulate something a bit more precise. So to a complex integrable system, of Seiberg-Witten type, one can associate a family, let me denote it like this, m zeta omega 2 zeta of complex symplectic manifolds parameterized by by zeta which belongs to CP1, although infinity is not important, it can be just a fine line, such that this has a pole of degree. Okay, let me put just C. Otherwise, I will save some chalk. Has a pole of degree 1 at zeta equals 0. Second, m zeta form a local system of local system over C star, and the fiber at 0 fiber at zeta equals 0 is the dual integrable system. So dual means that a generic fiber is a dual abelian variety. For example, if we start with an integrable system, so it's a dual abelian variety. In particular, to a complex integrable system, which means, so let me put the notation here, whatever. Yeah. So then, since it's an integrable system, the fiber is a complex torus, so let's assume for simplicity that it's polarized abelian variety. So it's dual to this. And so the remark is that a special case, if we have a Hitchin, which is a complex integrable system of Seiberg-Witten type, then the fiber at 0, M0, corresponds to the dual Langlands group. Hitchin, like G Hitchin, where G is a group, so to GL Hitchin.
But you said that the form has a pole at 0, so what do you mean by?
Yes, it's not, yeah. So this is a theorem.
No, I mean about.
So I will explain you what you'll get. Okay, so can you, Sash, can you wait a little bit? Yeah, okay. So I will explain what this means. at least at this time I can say you this means that there is a sort of a straightforwardly or almost straightforwardly defined local system over C star, and the claim is that under some conditions, and these conditions mean some convergency condition, you can compactify. Well, if you'd like, I mean, you can keep in mind this old construction of twistor space for this Simpson story, when you have this lambda connections, which I denote by zeta, so it should be called zeta connections. And so this is a local system over non-zeros, but when you compactify, so okay, so it's not just an analogy, because even in the case of considered by Hitchin, we have more. Excuse me, considered by Simpson, we have more. We can say more than he did. And for those who know this series of paper, at least one paper by Gayot, Amur, and Neitske on Hitchin SL2, this is sort of a more general result. Okay, now there is one more thing which I wanted to put here as a theorem, but there are some arguments in favor, but I don't know how to prove it, so let me call it conjecture. And the conjecture says that this m zeta for any zeta, non-zero zeta, are affine schemes of finite type over integers. So I will discuss later the arguments in favor of that, but a lot of things here depend on the intuition which one can gain from the mirror symmetry. So at this time it's not clear why. So second result, again, it's so next two results will be formulated in terms of some notions which I don't have time to explain, so I refer to other papers for the definitions. So if we have this local system over C star, then I can consider the algebra of functions. If they are, let's assume this conjecture, so then there are plenty of functions on the affine scheme. So this is an infinite dimensional vector space. And so we have a family of infinite dimensional vector spaces. And actually we can do the same thing in zero as well. So then the claim is that the family H zeta satisfies axioms of non-commutative exponential Hodge structure and here is a reference of Katsarkov, Kontsevich, and Pantyev, with one exception, with the exception that they are infinite dimensional. In their story, of course, they thought about cohomology of something. And here we look for algebras of functions, which of course gives many ideas on the possible relationship of this story with matrix integrals. I will formulate one conjecture later on about this relationship. And the last result, if I write here, is it okay? visible.
You write a bit larger than it is.
If I write larger, I cannot move it. Okay. 3. So we have a local system, so the monodromy of this local system, so let me skip of this local system about zeta equal to 0 is the automorphism of finite order. So it's birational. So in the case of Hitchin system, for example, I think it's probably general. Yeah, for Hitchin let me call it G system. It coincides, okay. With the Cox teratomorphism of the corresponding cluster variety. Cluster algebra. Corresponding cluster variety is the fiber. I mean, and zeta, it's they are all isomorphic for different zeta, so it's just local systems for Hitchin. So we know, for example, after Fock and Goncharov, that it's a cluster variety, and so as for the Cox teratomorphism, I can give you the reference in the case of cluster algebras, if I find it. Yeah. So Coxeter, so it's reference for this notion. So Coxeter for cluster algebras, but you can generalize. For example, it's a paper of Bing-Zhu in the archive. So this notion is related to the notion of Bernstein, Gelfand, and Ponomarev reflection functors being translated to this Fomin and Zelevinsky framework. All right, so these are some results, and now I explain you how one can think about integrable system from the point of view of mirror symmetry. So basically, what intuition we can get if we employ Ströminger and Yauer approach to. So where is the eraser? I put it somewhere, but I forgot it. Actually, I'm not sure that.
Where?
Ah, yeah, it's here. Yeah. Okay, thank you. All right. So the slogan is the following. So real integrable systems, they correspond to collapsing Calabi-Yaos. I put two-sided arrows, but technically so far it's just in one direction. So collapsing general Calabi-Yaos, complex integrable systems, collapsing hyperkähler varieties. So, and the guiding line is a Ströminger-Yau-Zaslow approach, or better, its version which we suggested like more than 10 years ago. In this paper, I give archive references because I don't remember where it was published, and then it was further developed in our paper 2004. So what means collapsing? Collapsing means the following, that we have a family of, say, n-dimensional, complex n-dimensional Calabi-Yaos, which degenerate, well, over the disk, which degenerate at 0, and this is a maximal unipotent degeneration. Which means that the monodromy has a maximal unipotent block, which means of the size n. So since they are Calabi-Yau, so we can look at this story not algebra geometrically, but as differential geometers. So we have a family of Riemannian manifolds, and they have Ricci curvature which is 0, and so we can assume that the diameters of these Riemannian manifolds are all the same, because we can rescale the metric without affecting Ricci curvature. So we are in position of Gromov's theory. We have a family of metric space of Riemannian manifolds with Ricci curvature bounded from below and diameter bounded from above. So then we conjectured in this paper, and it's been checked in the non-trivial example of K3 surfaces by Gross and Wilson, that the following is true, that xt converges as t goes to 0 in Gromov-Hausdorff sense as a metric space to some metric space which satisfies some nice properties. So first of all, there is an open dense submanifold, smooth submanifold, Riemannian submanifold of this metric space, such that its complement, which means a singular subset, has codimension at least 2. Secondly, this smooth part carries an integral affine structure, and there are some conditions on the metric, on the Riemannian metric, which let me skip. Basically, it says that the Riemannian metric satisfies the real Monge-Ampere equation, which means that in the affine coordinate, determinant of the matrix of the metric is constant. Okay, so this is a conjecture which still open, but if we assume this conjecture, then we see that with the collapsing maximally degenerate or collapsing family of Calabi-Yaus, we can associate a real integrable system in the trivial way, at least for the smooth part. So since we have an affine structure, so we have a covariant lattice which gives this affine structure, and so we have the torus fibration. With the fiber, let me put dual since we have a metric. So this is a dual lattice. So we have an R-integrable system. And similarly, for complex, for hyperkähler, everything becomes complex. So there is a complex structure here. Okay, and of course, I mean, this conjecture is a little bit more involved in the original paper. Of course, a mirror dual family converges to the same base, but the affine structure is dual, which of course corresponds to dualization of this torus fibration. Okay. So this was a conjecture which we make here, and in this paper, which was later generalized, although in slightly different framework by Gross and Siebert, we asked for the following question: if we know just the base with affine structure and singularities, how we can reconstruct this Calabi-Yau, which from our from the point of view of integrable systems, so we want to reconstruct everything working in the manifold with probably singular affine structure. Singular, the singularities in this singular subset of codimension. All right. So, and the reconstruction procedure, of course, it's just basically the construction of mirror dual, since we can freely dualize. So if we can do it for this, we can do it for dual. So then, so construction of mirror dual, which was suggested in this paper. It consists of two steps, and this is relevant for this integrable system story. First, it's construction of naive, or let me call it semi-flat dual. And this semi-flat dual is a complex manifold. And secondly, correction, let me call it semi-flat maybe. Semi-flat dual. Correction, this X semi-flat to the honest dual by wall crossing formulas. Okay, we can, these two steps are very general. They do not depend on the origin, which means that we should not start with some collapsing Calabi-Yaus or something like that. And basically the data which we are talking about is the following. Let me call it like semi-flat data. We have them in the mirror symmetry story, we have them in integrable system story. So we should start with a topological manifold B, which contains a smooth manifold, open dense B smooth. So local system of lattices on this smooth, which you can think of in the integrable system case as that local system of integer cohomology of fibers, closed one form with values in the dual local system, and this closed one form should satisfy the non-degeneracy condition, which means that the map for every point, this map should give an isomorphism with a cotangent bundle, with a cotangent fiber, so which basically means that alpha defines an affine structure on B, of course. And the last piece of data, which is not visible neither in mirror symmetry, if we understand it, like I said, or in integrable system, it's a torsor, so smooth. In the real case, it's real torsor M over the torus. So let's discuss this data. So how they appear? Suppose that we want to construct the mirror dual starting with this naive approximation with the torus vibration. Then the first approximation is semi-flat dual should be the set of Lagrangian fibers endowed with U1 local systems. Well, certainly it's a torsor, but it's a trivial one because we can consider trivial U1 local systems, so it has a section, and in the case of mirror symmetry, this torsor is trivial. But here I ignored the B field, and you can imagine that if I consider the collapse with the presence of a B field, then this torsor can be non-trivial. And in the case of integrable systems, there is no reason for the local system of first integer homology to have a section. So then in general, this torsor, although it's not explicitly formulated, but it's visible. So, and the lemma says that the total space of this torsor M carries a complex structure so indeed it's just an exercise. Okay, so how to think about this semi-flat dual? So one way to think of it is first to look at the Fukaya category of the total space of the integrable system. And this is the place where we can spend another hour discussing the conditions when the Fukaya category exists. Yeah, I understand we don't have this hour, but theoretically we can. And the point is, so we have, say, a real integrable system, yeah? And so first question whether there exists a Fukaya category, because if it exists, then we can look for the space of object, and what we do is just some open subspace in the space of objects. So then if you believe that it can be defined, so if B is compact, then the problem with the definition is basically the problem with singular fibers. If B is non-compact, then there are more problems because one needs to impose some convexity conditions at infinity to ensure that there are no pseudo-holomorphic disks which go to infinity. But again, these are hidden under some assumptions. And so then first what we started with is just considering some open subspace in the space of objects of the Fukaya category. But then comes the second part, which means the wall crossing. And the point is, even if B is compact, then the problem with singular fibers is that this exists only over the non-singular story. So in order to consider Lagrangian tori, we must be sure that they are non-degenerate. And so the question is how to compactify. And this is a non-trivial story, which indeed employs the wall crossing formula. So let me discuss it somehow in the case of complex integrable systems corresponding to Calabi-Yau threefolds. But before I will do this, let me tell you that if this is a complex integrable system, then we can do the following. We can take the complex symplectic form, we can rescale it by any non-zero complex number, and consider Fukaya, which corresponds to this symplectic form. Yeah? So since it comes from complex and it has pole of order 0, of order 1, so this maybe explain you that the question of compactification is non-trivial. So the imaginary part of this story comes as a B field, appears as a B field, which gives you this non-trivial torsor M from the semi-flat data. But so, since zeta is arbitrary, this means that we have a family of such semi-flat data, and when I discuss wall crossing formulas, you should, in case of complex integrable system, think that we can do this wall crossing in a uniform way for each zeta, and so the result, it will be not just one space, say one mirror dual, but family which depends on the parameter zeta. So I don't have time to discuss wall crossing formulas, but I believe that there will be other talks or people know what is this, so I will be brief, but I will make some connection with geometry. So corrections by wall crossing formulas, and I consider a special case when my B is a Lagrangian cone, so X is a Calabi-Yau threefold. I will not specify whether it's compact or non-compact, although it's important. Well, I will explain maybe why it is important, but let's assume that it's non-compact, like local Calabi-Yau. And this is a moduli space of, I don't remember like called, gauged Calabi-Yaus. It parameterizes pairs a complex structure and the corresponding holomorphic free form. So then certainly it's a C star fibration over the moduli space of complex structures. And it's a Lagrangian cone, complex Lagrangian cone in this symplectic space. And furthermore, there is a projection, like imaginary part of the holomorphic form, which gives an affine structure. This is a local homeomorphism, so we have an affine structure here. And in particular, what we can do, we can, on this cone, we can draw tropical trees. Tropical means that their edges are integer lines with respect to this affine structure. So the general story is the following for the integrable system. So we have integrable system, and there are some points where the fibers degenerate. So like imagine that it's an elliptic fibration, like for Seiberg-Witten, and we have for Seiberg-Witten SU2, we have 2 points, yeah, where these elliptic curves degenerate, which means on the base we have marked point and the homology class of the vanishing cycle. For Calabi-Yau threefold, we have the same story. It's called conifold point by physicists. And this gamma like imagine that it's like vanishing Lagrangian 3 sphere. Okay, so then we have the bunch of conifold points in this case, or some conifold subvariety, and the directions. So for local so what I want to do next, and what is a part of the construction, so I want to construct some space. So remember I started with some semi-flat dual and I want to correct it. So, and this correction depends on Donaldson-Thomas invariants, which means that to every point B and to every integer direction gamma, I want to associate an integer number called the Donaldson-Thomas invariant. And the initial conditions are just these singular conifold points with the direction, with the homology classes of vanishing cycles, either three-dimensional spheres, so in one-dimensional, it's just one-dimensional cycles. And this is an inductive procedure which was, well, physicists understand it in the language of what's called split attractor flow of Deneuve. Again, like 10 years old story. But mathematically, what we do the wall crossing. So, for example, if we have 2 points with 2 homology classes of vanishing spheres, so we have these 2 lines, and suppose that these 2 lines meet somewhere on the base B, on this Lagrangian cone. So then, theoretically, we can have infinitely many lines of all possible rational slopes in this 2-dimensional angle. So then the wall crossing formula, it reads like this: a certain identity of automorphisms in the group of symplectomorphisms of this torus associated with the homology lattice. So the wall crossing formula, it reads like this. Here we have infinite product of all these T gammas, and T gamma are certain. It's a certain basis. It's some standard birational transformations, some cluster transformations of this torus. So this is an infinite product. Now, from local considerations at the conifold points, these omegas are equal to 1. It's just monodromy considerations, which are obvious in the case of curves. So then we know the left-hand side, and from this equation we can derive all possible omegas in the right-hand side. So then the procedure, if you want to compute omega corresponding to the point B in the base of integrable system, so this Lagrangian cone, and the direction gamma, we simply look for all possible trees, tropical trees, which has external vertices at the conifold points, and which arrive to the given point with the last leg having a fixed direction. So under some assumption, this is a finite procedure, and this is non-trivial that it's finite. But then we have, let's call them Donaldson-Thomas invariants associated to every point of B. So if you look from the categorical point of view, this Lagrangian cone is a part of the space of stability conditions on the Fukaya category of X. Yeah, and the central charge is given by the period map of the holomorphic 3 form. So equivalently, you can see that these edges of these tropical trees, they are gradient lines for the square of the absolute value of this period map. All right, but then having these numbers, we can apply the machinery. I don't have time to explain it. I have just a few minutes. The machinery which we outlined here, and construct and correct the semi-flat space. So then, if it's done, and if it's done for every complex number zeta, then we have so using wall crossing formulas for all complex zetas, we arrive to the corrected, well, X dual, which this is what I call this M zeta, which is still present on the blackboard. All right. Now I don't have time to discuss why we can compactify and why it is dual, but let me just mention one piece which is related to this theorem too. Part of the axioms of Katsarkov, Kontsevich, and Pantev non-commutative Hodge structure is the existence of so-called Stokes filtration. So it's part of the story which one needs to have in order to define this non-commutative Hodge structure. So Stokes filtration appear from this point of view in a very natural way, and it's related to the old work of Simpson on the asymptotics of monodromy of the local system. So you can imagine something like this. You consider this is a small parameter, and you consider flat sections of some local bundle, and you look for the monodromy as a function of zeta, and the question is how it behaves as zeta goes to 0. In differential, people doing differential equations know it under the name of resurgence condition. So it's well, this Stokes filtration is very much related, and in a sense it's a generalization of this story. So you look, we have a family over zeta, yeah, this local system, and let's consider analytic path which hits a 0 fiber. So some field zeta. Then we can take any function on the fiber restricted on the path and look at the asymptotic, for example, trace of the monodromy to make a connection. So one can show that the behavior it's more or less like some numbers divided by zeta, and these exponents give the filtration, which is a Stokes filtration. Just one comment about finiteness condition. These are affine schemes, M zeta, at least conjecturally. So the multiplication for this M zeta, it can be derived from the considerations in the Fukaya category. Since there are no higher X groups, we can look for the corresponding dual Lagrangian zero section, which is B, and look for homes in the Fukaya category from B to B. So this is exactly ORF M zeta. Recall that it's a local system, so they're all the same. I can consider zeta to be an arbitrary. And it's a very non-trivial thing, because this computation involves counting of pseudo-holomorphic disks. And so Maxim told me yesterday that he made some computations in a very simple case, and they are very highly non-trivial. So, but what comes as a result of this computation, that this O of M zeta, these algebras of functions, they come with a basis, and this is a basis which probably appear in the work of Fock and Goncharov on cluster varieties. It corresponds to integer points of the affine structure on the base. Okay, so I'm run out of the time. So I have also one more conjecture on the relations to matrix integrals, but since I don't have time, probably I should stop.